Good morning, class, and you're welcome again to Chemistry 121, Introductory Chemistry 2. Today, we'll be looking at Valence-Shell electron-pair repulsion theory. We'll be looking at shape of simple molecules that are formed in covalent bond. You will recall that in one of the classes, when we are looking at covalent bonds, I mentioned that covalent bonds are directional. So covalent bonds, they are directional. The implication of that is that covalent bonds have shapes, specific shapes, and the shapes are determined by Valence-Shell electron-pair repulsion theory. So Valence-Shell electron-pair repulsion theory is used to explain the shape that a molecule will attain. So each group of valence electrons around the central atom is located as far as possible from each other so as to minimize repulsion. So one of the concepts of the theory is that electrons repel themselves. So as the name sounds, Valence-Shell electron-pair repulsion. So each electron in the central atom repel each other. So it's arranged in such a way that it is as far as possible from each other. Then the second concept is that a group of electrons in any number of electrons that occupy the localized region around an atom. What that is trying to say is that when you have an atom that is a central atom, there is a grouping of the electrons as they occupy a localized region. When we get to the depth of the theory, you will understand what I'm trying to say here. So a single bond or a double bond or a triple bond that is formed will be based on this concept of Valence-Shell electron-pair repulsion theory. So it is possible for the valence electron to form either a single bond or a double bond or a triple bond. Then you can also have lone pairs of electrons. Lone pairs of electrons. So a single bond is a group of bonds, double bond, a group of bonds, triple bond, a group of bonds, lone pair, a group of bonds, and even you can have a single electron as a group of bonds. Now, to be able to understand Valence-Shell electron-pair repulsion theory, I will start from what you understand previously, which is hybridization. At O level, you are taught hybridization. You are familiar with sp hybridization, you are familiar with sp2 hybridization, you are familiar with sp3 hybridization. The one you are not familiar with is the sp3d and the sp3d2. Now, sp hybridization will give you a linear molecule like you have in this case. Sp hybridization will give you a linear molecule. So when you see a molecule undergo sp hybridization, it will be linear. The angle in linear molecule is 180. So you have a 180 angle between the central atom and the terminal atoms. Then in sp2 hybridization, you have a trigonal planar structure. A trigonal planar structure. And in trigonal planar, you have the angle between the central atom and the terminal atoms to be 120. All that you have learned in O level. Then, when you have an sp3 hybridization, in an sp3 hybridization, you have a tetrahedral structure. And in tetrahedral structure, the angle between them, the central atom and the terminal atoms, is 109.5 degrees, 109 degrees, 28 minutes. Now, the ones you have not been familiar with is sp3d and sp3d2. In sp3d, you have a trigonal bipyramidal structure. A trigonal bipyramidal structure. In trigonal bipyramidal, you have a trigonal base and you have a pyramidal axis. So this base, this diagonal base, is called the equatorial axis, and you have the non-equatorial axis between the central atom and the equatorial axis. You have a 120-degree bond angle, but the non-equatorial, you have a 190. If you look at the number of terminal atoms that you have around the central atom, you have a total of 1, 2, 3, 4, 5, because an sp3d hybridization. So you have one sp orbital, 3d orbital, 3p orbital, and 1d orbital hybridizing to give you 5 hybrid orbital. That is an sp3d hybridization. So you have that to be the representation. Then the last one is the sp3d2 hybridization. In sp3d2 hybridization, you have an octahedral structure, which is fixed. So you will see that you have the square planar axis that has 1, 2, 3, 4, and you have the vertical axis that has angle 90. All of them, you have angle 90 as against the trigonal bipyramidal. So in sp3d2 hybridization, you have 90 to be the angle between them. Now, to be able to further understand what we're trying to talk about, I will quickly list some of the molecules that have all these hybridizations, and we will now probably look at few of them to explain what we're trying to talk about. In sp hybridization, you have beryllium fluoride. So beryllium has 1s2, 2s2. Now, when it wants to form hybrid orbital, you have the s orbital and you have the p orbital that has 3 subshells. Now, you have one of the electrons in the s orbital, and you have a promotion of one of the electrons into the p orbital. The second electron in the s orbital is promoted into the p orbital. Then you have an hybridization of the s and the p to give you an sp hybridization, and that will now give you a dumbbell system. So you now have fluorine coming around here and the other fluorine coming around here to give you a BEF molecule, a BEF molecule. Now, that is what happens in sp hybridization, and you will see that this is a linear molecule. Another, the next one is when you have sp2. In sp2, like you have in the case of boron, you have s orbital and you have p orbital. You have one electron here Then there is a promotion of the second electron here because of the concept of repulsion. Electron-pair repulsion. Instead of it to have a pair here, it is repelled and you have it there. And you have the other electron that is already in the p orbital. So you now have an hybridization of this to give us an sp2 hybridization that is a trigonal planar structure. So you have your boron at the center and you have your fluorine as your axis atoms. So you have your fluorine as your atoms that are flanked around that. So you have sp2 hybridization by that repulsion. Now, you know that of carbon, so I will not necessarily go to sp3 hybridization of methane. You've been taught that in O level. You have a tetrahedral structure. So I will go to that of sp3d. In the case of sp3d, you have these to be your phosphorus. So I want to use phosphorus pentafluoride as the example. In this case, you have an f orbital, you have a p orbital that has 3 subshells, 1, 2, 3. Then you have a d orbital that is close to the sorry, please. Let me clean that. So you have, please, sorry. You have a d orbital. You have 1, 2, 3, 4, 5. Now, in this d orbital, for phosphorus, one of the electrons will be here, which is the electron of the s2. Then you have 3p already. So you have 1, 2, 3 in the p orbital. But don't forget that the theory is Valence-Shell electron-pair repulsion. So there's a repulsion of the electron here into any of this space. So you have the electron coming into that space. Now, that electron that came into that space, so you have an hybridization of 1 of the S, the 3 of the P, and 1 of the D. So you have an sp3 hybridization, and that will give you a trigonal it will give you a trigonal bipyramidal. Trigonal at this age. So you have your phosphorus at the center, and you have your fluorine flanking it like that. Your fluorine has terminal atom around it in that group. As was previously said, you will have, you have 90 between this angle and this angle, and you will have 120 between that. No, so that explains sp3d. Then sp3d2 is octahedral, and you have for sulfur, you have sulfur to be in that form. You have 3 subshells for P, and you have 5 subshell for D. So you have 1, 2, 3, 4, 5. So the electron in s orbital of sulfur, you have 1 like that. The electron in the p orbital of sulfur, this is sulfur. So this is the one that you have. You have 1, 2, 3. Under normal situation, you are supposed to have another one in the p orbital, but electron-pair repulsion. So it was repelled, and you have that. Then you also supposed to have another one in the p orbital to make it 4, but electron-pair repulsion, you have that. You have that. And as a result of that, you now have an hybridization of s orbital, p orbital 3, and 2 of d orbital to give us an sp3d hybridization that is an octahedral structure. So you have something like that. Then you have that. So your sulfur here now, your fluorine here attached to the sulfur will now be attached in that way around the molecule, around the molecule. Around the molecule, the central atom. So you have your sulfur as your central atom. Then you have that to be the way the molecule will be. So you have an octahedral structure in this form. Now, I have explained from the simplest. So these are the simplest. These first ones are the simplest. But we have those ones that are on the same, they are on the same page with the same molecule nature, but they do not follow the basic explanation I have talked about. But I will still come back to them as we move on in the course of the class. So if you look at ammonia here, you will see that ammonia doesn't have 4 terminal atoms attached to the central atom. We'll explain why that is. So what I've just explained is what is now here, using carbon, which is a simple example. You have carbon to have 1s2, 2s2, 2p2. But because of electron-pair repulsion, you have a repulsion of this electron from this point to a higher point. So you have this electron promoted, and you have that up. Now, when you have that, the output is that you now have sp3 hybridization. So sp3 hybridization will give you that. So you have a tetrahedral structure. So 1 s orbital and 3 different p orbital. S orbital is spherical and p orbital is dumbbell. It will now give you a tetrahedral sp3 hybridized orbital. It will give you an sp3 hybridized orbital, which is what you have there. So you have s orbital now forming, sp3 orbital now forming 4 bonds with hydrogen, 4 molecules of hydrogen to give you methane. Then you can also have a situation where the hybridization is an sp2 hybridization, 1 s orbital and 2 p orbital to give you 3 hybrid orbital that is an sp2 hybridized orbital. So you now have 1 hydrogen atom attached to each of the sides of the 3 trigonal system to give you what we have as our product there. Then you can have the last one, which is an sp hybridized orbital. So it's a linear hybrid that has 180 degrees bond angle. So what then is the real concept that we want to learn? The concept that we want to learn is that electrons are arranged in the hybrid orbital. So the electron group arrangement is defined by both bonding and non-bonding groups. It is not just the bonding group that determine what happens in the shape of molecules. The shape of molecules are determined by the arrangement of the electron. And the general molecule shape is AXM EN. A is the central atom. X are the axis or the terminal atoms attached to the central atom, where E is the non-bonding electron. The non-bonding electron. N and M are integers, so they have to be positive values. For instance, if you have AX2 E1, it means that you have two terminal atoms and you have one lone pair of electrons, one electron, that is attached at the lone pairs of electrons. So generally, we always have this concept of what we call the AXMEN. So anytime you see a molecule, you ask yourself, what is it, AXM or is it AXMEN? Is it AXME values and things like that? So we will look at specific examples of what I'm talking about. Now, we want us to look at the specific examples of AX. Now, when you have whether AXM or AXME, it's also determining the bond angle. You know that we mentioned that there is always a bond angle that could be either 120, 180, 120, up to 90, depending on the hybridization. But when we have, for instance, let's use a trigonal planar structure to serve as example. In this trigonal planar structure, you have A to be your nucleus central atom, and you have 3x. So this is an AX3 system. It's an AX3 system. There is no electron pair that is a lone pair in this case. Now, the angle between this is 120. The angle between this is 120. When you have that situation, you have the real and ideal situation. You have the real and ideal situation. So the angle will be 120. But the moment you have a double bond, the moment you have an introduction of a double bond, the double bond will create a change in the bond angle. It will create a change in the bond angle. So the real is not equal to the ideal. Then, in any case, when you have another electron repairing species, it can also affect the bond angle. You have the real not equal to the ideal. Then, when you have a lone pair, you have a different situation. So we have different deviations from the regular SP will give you straight line molecule. SP2 will give you a trigonal trigonal planar structure, and all those that we've mentioned previously. And each of these deviations, we will need to look at them one after the other. Now, so we will start with AX arrangement. In AX arrangement, you have only sp hybridization. But you can have other ones that are not sp, that are distorted forms of others, which we are going to look at with time. But the bond angle between them is 180. So in AX2, the bond angle is 180. The central atom is your A. The axis atom is your X. And you have 1 of and 2 of X, and you have 1 of A. Typical example of molecules that exhibit this linear structure is CS2, HCN, and BeF2. Now, in each of these cases, you have sp3 hybridization, but you can have another, that you can have distorted form that will also give you linear molecule, which we are going to see in other slides. Now, the next one is a trigonal planar structure. In a trigonal planar structure, you have commonly, you have sp2 hybridization, which will give you an angle of 120, your central atom being A, your terminal atoms being X3. So you have A to be your central atom, X3 to be your terminal atom. Now, this is the general real, but the ideal that is not real is this, that we are going to talk about soon. Now, examples of molecules that exhibit sp2 hybridization that is trigonal planar is boron trifluoride, sulfur trioxide, nitrate, and carbonate. All these will undergo sp2 hybridization, not sp3, sp2 hybridization, that is trigonal planar. But a deviation that you have sp2 hybridized orbital, but it has a lone pair. So you have S2E. Instead of you to have AX3, you have AX2E. The E here is the lone pair. And this lone pair will stand in one of the position of S. And as a result of that, you have a V shape, a bent shape. So this molecule, when you want to write it, you write it as V shape or as bent shape. Molecules that exhibit this property are sulfur dioxide, ozone, lead dichloride, and thin dibromide. Now, if you look at all these three, they will undergo sp2 hybridization that's supposed to give you a trigonal planar, but one of the trigonal planar points, either this or that, is now having a lone pair, making it a bent shape. You would recall that when we were looking at ozone in previous class, we did not write ozone as a linear molecule. We wrote ozone as a bent molecule. When we want to write ozone, it is incorrect to write ozone like this. It is incorrect to write ozone like this. This is incorrect. If you want to write ozone, you write ozone like this, because ozone is a V-shaped molecule. The oxygen here is sp2 hybridized, but the lone pair of electron on the ozone will stand in that form as a lone pair, and you have a V-shaped molecule and not a straightforward straight line molecule. We'll look at the sp3 hybridization and the like later. But let's look at what happens when you have a lone pair, like we did in the case of AX2E? In this case, we have thin dichloride. In thin dichloride, you have an sp2 hybridization. It's supposed to be a trigonal planar structure. So you have this, and that. The angle between them supposed to be 120 degrees Celsius, not Celsius, 120 degrees bond angle. Now, but because of this electron pair, don't forget our concept is Valence-Shell electron-pair repulsion theory. Because of this electron pair, you have a repulsion of this bond and a repulsion of this bond. Now, these two repulsions would now reduce this angle to 95 as against 120 that's supposed to be the bond angle between them. So you would see that one factor that affects the positioning, the angle, the bond angle, is the presence of a lone pair. So the presence of a lone pair plays a significant role in what you have as the shape and the bond angle of your molecule. When you have a double bond, I said that double bond also plays a significant role. So when you have a double bond like you have here in this case, the angle is supposed to be 120, 120, 120, because this carbon is an sp2 hybridized orbital and it's supposed to be trigonal planar structure. The bond angle, the double bond creates a repulsion and it repels this and expands this. It repels this and expands this. So you will now have 122 instead of 120, and you have another 122 instead of 120, and this becomes 116. So the presence of this double bond is repelling, because this is an electron system, is repelling this bond and repelling this bond and reducing that bond angle. So in the ideal, you have 120, but in the non-ideal, the real situation, you will have 122, 116. So you have the presence of lone pair and the presence of double bond affecting the arrangement. Now, the next structure or the next hybridized orbital is the sp3 hybridized orbital, which is an AX4 shape. AX4 shape will give you a tetrahedral structure. That is a normal AX4 shape. It will give you a tetrahedral structure. And this structure is what you have for the likes of methane, silicon, trichloride, sulfate, chlorate. In this case, each of these central atoms will undergo what we call sp3 hybridization and give us an AX4 structure. So the AX4 structure is tetrahedral, and all these are all tetrahedral. They will undergo sp3 hybridization. In the case of AX3E, you have a lone pair introduced into that structure. It's supposed to be AX4, but you have a lone pair, which is E, introduced. That lone pair would then give you a trigonal pyramidal structure, which is different from a trigonal planar structure. This is a pyramid, a kind of a pyramid with a trigonal base. So that is what you have in the case of period 5, nitrogen and phosphorus. Nitrogen in ammonia and phosphorus in phosphorus trichloride will give you this sp3 hybridized with a lone pair on it. Now, if you look at this trichloride and trichloride, trioxide, and a tetraoxide of chlorine, you will see that you also have a reduction of, you have an sp3 hybridized orbital with a lone pair, and that lone pair is making this to be a trigonal pyramidal structure. The same thing with hydronium ion. That is also a trigonal pyramidal structure. In the case of, you can have the third scenario. These are ideal. This is the ideal scenario. These are the real scenario. The case of X3E and the case of X2E. In this case, you have two lone pairs of electrons. You have an sp3 hybridized orbital, and you have two lone pairs of electrons. These two lone pairs of electrons would then make this shape to be a bent shape. It will now be a V shape, a bent shape. That is the reason why you will never see a situation where water is written as a linear molecule. Water is written as a V molecule. You have your oxygen in the center, and you have your hydrogen attached to it. So water is never written as a linear molecule. Water is written as, so water cannot be written in this form. This will be wrong to write water like this. It will be wrong to write water as a linear molecule. You write water as a bent molecule. This is wrong. This is what is right. So in any case, what we are trying to say is that water is sp3 hybridized orbital that ideally should be AX4, but is AX2E. The E is as a result of lone pairs of electrons that you have in the molecule, and that lone pair of electrons will create that bend. As a result of that, you also have other molecules to have different bond angle, which we are going to talk about later, compared to the other ideal situation. Then you also have OF2 and FCl2 to be molecules that are within that same category. So we will look at the issue around it later. So when we were drawing Lewis structure, we draw Lewis structure like that, but that is not the real way the molecule exists. We draw the molecule in this form, but the molecule actually exists in a discrete directional form. A discrete directional form, like you have, this is tetrahedral. Now, if you compare this with this, when you twist the diagram, if you twist this diagram in a clockwise and anti-clockwise direction, you twist it to your right, anti-clockwise direction, this will give you this, and you will see that this doesn't look like that. This molecule, this doesn't look like that. This underscores the fact that covalent compounds are directional in nature. They have shapes that are directional in nature. The next one is the trigonal bipyramidal, which is an hybridization of sp3d. sp3d will give you 5 bonds, 5 hybrid orbitals. Now, you are supposed to have this to be the structure in the ideal state. So it should be AX5. The A is the central atom. Then you have 5 X terminal atoms attached to it. Okay, so you will have phosphorus to be your central atom, and you have your terminal atoms as presented. Now, phosphorus, pentafluoride, arsenic pentafluoride, and copper, oxygen trifluoride, tetrafluoride, are all sp3d hybridized orbital, sp3d hybridized orbital with each of them having 5 bonds that is resulting from that. But this is the ideal, which which follows the ideal, and these molecules follows the ideal concept. But you have the exceptions, the real. You have 3 of such, 1, 2, 3. In the fourth case, you have what we call the seesaw. The seesaw, you have an sp3 dehybridized orbital, but there is a lone pair. And in the case of trigonal bipyramidal, the lone pair are always on the equatorial axis. This is the equatorial, the one that is the planar, the trigonal part, the trigonal planar part. So this axis. So if you substitute one of the trigonal part with a lone pair, then you have a seesaw structure. And that is AX4E with one lone pair. Molecules that that follows that are presented on the slide. You have SF4, XeO2F2, IF4 plus, IO2F2 minus. You will see that all of them, the central atom has four axes or 4 terminal atoms attached to it, because there is a lone pair that is already occupying the space. Then you have the second real situation, the second deviation. In the second deviation, you have chlorine as your central atom. The chlorine as your central atom is also undergoing sp3 dehybridized, it's an sp3 dehybridized orbital. And in any case, you have a trigonal bipyramidal, but you have a deviation from trigonal bipyramidal by the presence of 2 lone pairs of electrons. And those 2 lone pairs of electrons are so represented. And because they will be on the equatorial form, so you have these 2. And as a result of that, you have a T-shaped molecule with only 3 bonds, 3 bonding electron pair and 2 lone pairs. So you have your fluorine coming around your chlorine in these 3 parts. And you also have it also in bromine trifluoride. So chlorine trifluoride, bromine trifluoride, they would be AX3E2 shaped. The other one, which is the last one, the last deviation in the sp3 dehybridized orbital, is a linear molecule. Now, this linear molecule would almost look like an sp2 hybridized molecule, but it's not an sp2 hybridized molecule, but an AX2E3 of sp3 dehybridized molecule. You have a trigonal bipyramidal structure that has 3 lone pairs. And don't forget, the lone pairs are not always on the vertical non-equatorial, but on the equatorial, equatorial. So you have 3 lone pairs, and you now have a linear molecule, as you have in XeF2, I3 minus. The I is like having high. This is not an appropriate thing, but I will just say you have one I with 2 I's attached to the one I, something that looks like that, but that is not really what I'm just using that to explain what I3 means. Then you have IF2. So you have 2 hydrogen, iodine atoms attached to one iodine atom that is a central atom. You have 2 fluorine atoms attached to one iodine atom that is central atom. You have 2 fluorine atoms attached to the xenon atom that is the central atom. So each of these would have what we call AX3E2 molecule shape, which is a deviation or a distorted a distorted sp3d hybridized orbital. Now let's go to the next example, which is sp. Okay, before we go to that, there is a need to explain the fact that you have the equatorial and you have the axial. The equatorial is where you have the substitution, then you have the axial to be above. In the equatorial, the angle between the equatorial is 120. The angle between the axial and the equatorial is 90. The axial is non-equatorial, and you have equatorial. So the last hybridized orbital that we'll be looking at is the AX6, which is an octahedral hybridization, octahedral molecule formed from sp3d2. S1, P3 making 4, D2 making 6. So you have 6 X attached to the central atom. Your central atom is that you have 6 flanks of terminal atoms, and you have an octahedral structure. And in this octahedral structure, S in this case, sulfur becomes the central atom, and you have 6 fluorine atoms around it. Iodine, your central atom, and you have 6 other atoms, 1 of oxygen and 5 of fluorine around it. So sp3d2 octahedral, angle between them 90, 90, all through both the equatorial and the axial, all of them the same value. Now you can have 2 possible distortion of sp3d2 hybridization, and one is AX5E. In AX5E, you have 1 lone pair of electrons, and that singular lone pair of electrons can be positioned either at this point or here. As a result of that, you have a square planar, square pyramidal structure. You have the square here, which is the base, and you have the pyramid like that. Or if the lone pair is positioned here, the pyramid will be down. So whichever case, you have a square pyramidal structure, and these are molecules that obey or that have that molecular structure. Then the last one is the AX4E2. In AX4E2, there are 2 lone pairs, and the 2 lone pairs are positioned on the axial, and you have a square planar structure, like in the case of XEF4, that's Xeon, and ICl4 minus. So you have a square planar structure in that case. Now, generally, what are the rules? Using the periodic table, period 2 atoms on period 2 can only form 6. You can only have either tetrahedral, a distorted form of tetrahedral that is trigonal pyramidal, or you have trigonal planar, which is sp2 hybridization, trigonal planar, or a distorted form of trigonal planar, which is bent shape, and you can then have an sp3 hybridization. So second period can only undergo sp3 hybridization, sp2 hybridization, and sp hybridization, which is linear. The other 2 here are the distorted form of either the distorted form of tetrahedral or the distorted form of trigonal planar. In the distorted form of tetrahedral, you can have, if you have only 1 E, you can have a trigonal pyramidal, or if you have 2 E, you can have a bent. In the distorted form of sp3, sp2, you can have one of them to be to the electron pair, lone pair, and you have bent shape. But for period 3 to 6 and also period 2, you can have, for period 2 to period 6, you can have a situation where, so for period 3 to 6, you can have a formation of all the bonds that we've talked about, all the molecules that we talked about, a trigonal bipyramidal, a seesaw, a square pyramidal, a T-shape, a square planar, an octahedral. All of them can be formed by the lower one. Why? Because you have the d orbital from the period 3 downward. Period 2 does not have d orbital. Period 3 downward has a d orbital. And don't forget that sp2d, sp3d, and sp3d2 are all the ones that can form these other shapes. These other shapes, and you can have distortion of them to form the shape in the cycle. Now, summarily, we've talked about all this. Linear molecules are AX2. Most often than not, the hybridization can be sp2 hybridization or distorted form of other. They exhibit AX2. The number of bonds that you can have to the central atom is 2 maximum, and the bond angle is 180. sp3 hybridization, sp2 hybridization can give you either of these two shapes. You can have AX3, AX2E. In AS3, you have 3 bonds. In AS2E, you have 2 bonds. In AX3, you have an angle of 120. In AX3 and AS2E, you have an angle reduced out of less than 120 because of the repulsion by this lone pair. This lone pair will repel that to give you a V-shaped bent shape. Then you have tetrahedral that can be these 3 possible shapes: tetrahedral, trigonal, pyramidal, V-shaped molecule. And the number of bonds 4, 3, 2, because of the fact that you have electron lone pairs already occupying those spaces. And the angle supposed to be in the real situation 109.28 minutes or 109.5 degrees, not Celsius. Then you have less than 109 because of this repulsion by this lone pair, and you can have less than 109 because of the repulsion as a result of that lone pair. As you move on, if you get to trigonal bipyramidal, which is an sp3 shape, in sp3d shape, in this case, you have 5 bonds, 4 bonds, 3 bonds, 2 bonds, depending on the presence of lone pair. This one has 1 lone pair, so it reduced to 4 bonds. 2 lone pairs, it reduced to 3 bonds. 3 lone pairs, it becomes 2 bonds. Then you have this to be linear, this to be T-shaped, this to be seesaw, and this is the original trigonal pyramidal. The angles between them are earlier mentioned. You have 90, 120, 90, 120, but because the axial is, removed to T-shape, then you have less than 90, then you have 180. These are less than 90, less than 120 because of the repulsion of these lone pairs of electrons. And the final summary is when you have an octahedral shape that is sp3d2, resulting from resulting in 6 bonds, 5 bonds, and 4 bonds. 5 bonds and 4 bonds because of the lone pair that has removed 1 bonding pair, and the lone pair that has removed 2 bonding pair. You have a square planar, a square pyramidal, and octahedral. You have less shapes as you move, less angle as a result of the lone pairs. Now, in this case, there is no less angle because the repulsion of this is countered by the repulsion of this. This is repelling, this is repelling, this is repelling upward, this is repelling downward. They cancel each other and give you a bond angle that is 90. Now, we talked about this previously. When we draw Lewis structure, this is how we draw it. But now we want to introduce the molecular shape. When we are drawing Lewis structure, we follow this step. But at this point, we want to introduce how that affects the molecular shape. So we will start with phosphorus trichloride. In phosphorus trichloride, you have this to be your Lewis structure. So the ideal angle, the angle supposed to be 120 in between them. The angle supposed to be 120 in between them. There is an error here. The angle supposed to be 120 in between them. But the angle is less than 120. The angle is less than 120 because of, sorry, there's no error there. Something is correct. It's tetrahedral. The phosphorus there is undergoing tetrahedral. So this lone pair is repelling that. So there's no error. You have, it's not an sp2 hybridized orbital. It's an sp3 hybridized orbital. sp3 with a lone pair of electrons. This lone pair of electrons is then repelling this other bond. And this is going to be a trigonal pyramidal structure. It's supposed to actually, this is a Lewis structure. If you are drawing it, it's supposed to be something like this. It's supposed to be something like this, but you now have a lone pair here. It's supposed to be tetrahedral, but you now have a lone pair here, and this lone pair is now repelling these other bonds to give you what you have in this case. So the angle is less than 1095 degrees because of the repulsion of this lone pair that you have here. So you will see that the arrangement, the structure is a trigonal pyramidal structure. You have this to be the Lewis structure, but this is the real structure in space. It's supposed to be a tetrahedral arrangement, but you have a lone pair there, and that lone pair is repelling this bond and making the bond. So the angle between them becomes 96.3 because of the repulsion of this lone pair of electrons that you have up there. Now, in the case of COCl2, you have a double bond. The double bond is the one playing the role here. In this case, it is a trigonal planar structure because it's an sp2 hybridization. sp2 hybridization. And in sp2 hybridization, you have a trigonal planar structure. In the trigonal planar structure, you have angles to be 120, but the double bond here is repelling these two angles that are supposed to be 120. So as a result of this repulsion, you have this angle increasing to 124.5, and this angle is reducing to 111. Now, this is a convenient point for us to stop the class for now. We will not be able to finish this class today. We will have to continue because our time is nearly up. We will have to continue the next time we meet, which is on Friday. However, I will just give you opportunity to say one thing or the other. So I'm going to unshare, or I'm going to stop sharing and unmute all of you. However, if you want to talk, I will appreciate if you raise your hand. If you want to say something, you can please ask your question very quickly before I close the class. I sent a chart on the chat box. I sent the link. If you look at the chat box, you will see the link for the class quiz that you do between now and Friday when we are meeting. When we meet on Friday, we would finish this part of the course. Can you, okay, I am Sheung Aduro Ja. You can ask your question very quickly.
Yes, sir. Can you hear me?
I'm hearing you.
Okay. As for the phosphorus.
For the what? You are not very clear.
The compound containing phosphorus.
Since your network is not clear, if you don't mind, send a chat. Any other person, your network is not clear, so I'm not hearing you. Any other person that has anything to say?
How about now?
Okay.
Sir?
If there are none, pardon me, I will have to stop the class here. We've spent our 1 hour. When we meet on Friday, we'll move on from where we stopped. Thank you and God bless.